So dear students, welcome to new lecture of control systems. In this lecture, we will discuss about the modeling of mechanical systems because later on this concept will be used to determine the transfer function of the mechanical systems. So we must know that how to model the given mechanical systems, right? Okay, so in this particular lecture, we will be discussing about a little bit of introduction to the mechanical systems, types of mechanical systems, and then modeling of mechanical systems. Okay, so what is a mechanical system? As you can see, a mechanical system is a set of physical components that convert an input motion and force into the desired output motion and force. So it is very simple that if we apply the force to any component, physical component, right? So if that force, so that motion is converted into the desired motion and desired force. So these are the mechanical systems. So okay, so there are various ways to categorize the mechanical system. One way is based on the motion. Okay, so if on the basis of motion, the mechanical systems can be categorized as translational systems and rotational systems, right? So what are translational systems? Those mechanical systems which move on a straight path, basically. So if the motion of a given mechanical system is along the straight line, so we call that particular system or mechanical system as translational system because such system possesses translational motion, like a car moving on a road, right? Or for example, if there is a table and some mass is kept on the table, and if you apply a force on this mass and if it moves along a straight line, so this is a translational motion, right? So now the translational system, they have three basic elements like mass, spring, and dashpot, or also known as damper. Mass, spring, and damper, right? So when we apply force to the translational mechanical system, that force is actually opposed by the forces due to the mass of the body, that is the system, the elasticity that is possessed by the spring, and then friction of a dashboard or damper, right? So these three, mass, elasticity, and friction, they oppose the applied force, right? So when you apply a force, so friction always act in opposite. And if we have a spring, so the elasticity of the spring opposes the force, and damper, the friction of the damper also opposes the force. Similarly, we have rotational systems, right? So the rotational systems are those systems which have a motion around or about a fixed axis. That is the system which rotates, which has some rotating part, like your motor, generator, tire, right? All these rotate about a fixed axis, and hence they have rotational motion. And because they have rotational motion, so we call them as rotational systems, right? So similarly, in these types of systems also, we have three basic elements: the moment of inertia, torsional spring, and again the dashpot or damper, right? So yeah, so here instead of force, we talk about torque, right? So when we apply a torque to the rotational mechanical system, then that particular torque is opposed by the moment of inertia, elasticity, and friction, okay, of the system. So now let us come to modeling of translational systems, right? How to model a given translational system. So when we have to model the given translational system, we have to see all the forces which are applied on the system and all the forces which are opposing that system, right? So this is what we have to see, because as per D'Alembert's principle, all these forces, that is the algebraic sum of all these forces which are acting on a system and opposing that force, is zero, right? So the applied force and the forces opposing the applied force, the algebraic sum of these forces acting on a system is zero, right? So now there are in case of translational motion, translational mechanical systems, there are three types of forces, and these forces are inertial force, damping force, and spring force. So these three forces resist the translational motion of the given translational system. Now let us see these three forces individually, how they act upon a system and what are their mathematical expressions, right? For example, there is a mass which is kept on a particular surface here, and if you apply force on this, so it will have certain displacement. So x here is displacement, right? And F is nothing but the applied force. Okay, so now this inertial force, it resists, it opposes the applied force. Okay, so this is because of the mass of the body, right? Now if a force is applied on a body having mass m, then it is opposed by an opposing force due to mass, which is we call as inertial force. This opposing force is proportional to the acceleration of the body, right? So it is F is equal to ma, right? So now if we assume that the elasticity and friction are negligible in this case, so we can say that the force is proportional to the acceleration of the body, where Fm is nothing but the opposing force, right? So Fm is equal to ma, where m is the mass of the body, a is the acceleration, and because a acceleration is equal to dv by dt, and where v is the velocity and v is dx by dt, where x is the displacement. So we have a is equal to d square x by dt square, right? So this is what we have got. So now these two forces have to be same, because the force that is applied minus the force which is opposing is equal to zero, as per D'Alembert's principle. As per D'Alembert's principle, these two forces, that is the algebraic sum of these two forces is zero, and hence we can say that the applied force is always equal to the force opposing the applied force. So they are equal and opposite forces, right? So it is given by this one. So if, okay, so when we have a mechanical system moving of mass m moving on a straight line, when some force is applied, so we can say that that force is equal to m and second derivative of the displacement with respect to time, right? So this is one equation. So we can use this equation further when we when we derive the transfer function of the given system. Now, what is damping force? So that is because of the damper or dashpot. A damper or dashpot, the symbolically is represented with this symbol here, right? So when we apply a force on the dashpot B, then this force is opposed due to the friction of the dashpot. Okay, and hence we can also call it as frictional force, right? So now in this case, this opposing force is proportional to the velocity of the body. Okay, this is proportional to the velocity of the body. Now if we assume that mass and elasticity are negligible, we consider these two factors as negligible, then this frictional force Fb is proportional to the velocity of the body, or Fb is equal to bv, where b is nothing but the frictional coefficient, right? So v, we know that it is first derivative of displacement with respect to time, dx by dt. So this is given by this equation. So this is the second equation of the mechanical systems. So we may have a mechanical system which combine all these three components like mass, damper, and spring. So in that case, we need to know individually that how these mathematically can be expressed, these systems mathematically can be expressed, right? Eventually, when we have to determine the transfer function of the given system, such type of system, so then we will combine all these equations and we'll try to frame a single equation, right? Okay, then we have spring force. So spring is a kind of element which stores the potential energy, right? So now in this case, if we apply, now this is a symbolic representation of spring. So when you apply force on this, so it is also displaced. I mean, there is a certain displacement here, right? Okay, in dashboard also you can see there is a certain displacement, right? Okay, so when we apply force, then the elasticity, it tries to restore the force. It tries to restore, right? Means it opposes the applied force. When you stretch a spring, it tries to restore back to the original position, right? So that means the elasticity of the spring tries to, oppose the applied force on it. Okay, though this opposing force, now this opposing force is proportional to displacement, right? And if we assume that mass and friction are negligible, okay, now why are we are considering them negligible? Because we are dealing with a kind of force individually. So we are assuming that other forces at that point of time are zero in this case. Okay, so F is proportional to X, where X is the displacement. If Fk is the opposing force, okay, because of the elasticity of the spring, then Fk is equal to Kx, where K is the spring constant, right? So we can say that F is equal to Kx, because Fk opposes F, then as per D Lambert's law principle, F minus Fk is equal to 0, or F is equal to Fk. So this is why we got this particular equation here, right? So now this these are the three elements, basic elements of a system, mechanical system with translational motion. And in similar manner, we have the basic elements of rotational systems also, right? Here also we can apply the D'Lambert's principle. However, here we talk in terms of torque, not in terms of force, right? So okay, so we can say that the applied torque and the torques which are opposing the applied torque, the algebraic sum of all these torques acting on a system is zero. So there are three types of torques that resist the rotational motion: inertial torque, damping torque, and spring torque, right? So let us see. Okay, this is in similar to the concept which we studied for the translational system. The only difference is that we are talking in terms of torque because it is got the rotational motion, and hence the notations, the symbolic representation has changed and the notation is changed here, right? So now uh, in translational mechanical system, the mass of the body or the system stores the kinetic energy. Similarly, in rotational mechanical system, the moment of inertia stores kinetic energy. So we can say that the mass and moment of inertia are equivalent. Mass for translational, moment of inertia for rotational, right? Now, if we apply a torque on the body having moment of inertia J, then it is opposed by an opposing torque due to the moment of inertia, right? So that means moment of inertia will oppose this moment of inertia, right? Uh, a torque which is because of moment of inertia that will oppose the moment of inertia. Now this opposing torque is proportional to the angular acceleration of the body. Okay, so that means if Tj is the torque that opposes the moment of inertia, right? So it is proportional to alpha. So Tj is J alpha, where J is the moment of inertia, alpha is the angular acceleration, right? And angular acceleration is second derivative of the angular displacement. Okay, so we have replaced alpha with d square theta by dt square, and T is the applied torque, Tj is the opposing torque. As per D'Alembert's law, T minus Tj is 0, so T is equal to Tj, right? Okay, so this is the equation for one element of the rotational systems, right? Similarly, for rest of the elements, that is the dashboard and torsional spring, the equations are given on this particular slide. So now this is the dashboard. Now, if we got some rotation of this, this element of the rotational system. So in that case, we can say that the torque that opposes the applied torque, TB is the opposing torque due to rotational friction of the dashboard, TB, right? So it is directly proportional to the angular velocity of the body. Okay, so TB is B into omega, and B where is the rotational friction coefficient, and hence TB is equal to B into omega, where omega is first derivative of angular displacement d theta by dt, and so TB is equal to B into d theta by dt. So T is equal to TB is equal to B theta by d theta by dt. So this is the equation, right? So we need to remember all these equations because eventually we would be using these equations to determine the transfer function of the given mechanical system, right? Now, similarly, we have the equations for the torsional spring, and we here say that it is the spring torque that opposes the applied torque on the spring, right? Okay, so when you apply torque on the spring, okay, so it is the spring torque that opposes that applied torque, and that force is proportional to the angular displacement of the spring. Okay, so we can take Tk is equal to k theta, where k is the proportionality constant and is known as torsional spring constant. So T is equal to Tk is equal to k theta. Okay, so now here we have all these six equations, basically three for translational and three for rotational. So these equations are very important when it comes to model a mechanical system. Okay, we must know these basic fundamentals, right? And because it would be easy for us to model a mechanical system and eventually to find the transfer function of the given type of mechanical system. So now this is it for today's class, and thank you so much.